Hi. Today we're going to be looking at question 6 for simple harmonic motion in IB. Okay. And this is going to be related to SL physics. Okay. Now, in this case, we have been given a velocity time graph, as we can see over here. So this is a velocity time graph. And they want us to find the corresponding acceleration time graph for this given plane. So the way we go about it is we have two ways. The first way, what we can do is that we can use a mathematical way. Okay, so in the mathematical way, we can sort of try to recognize this function. So in this case, this function specifically looks like negative cosine of t. And then if you take the derivative of the function, so d by dt of negative cosine of t, that would just come up to be positive sine of t, right? So one way is this mathematical way where you try to figure out what this function looks like for velocity. Then you take the derivative of the velocity to get your acceleration function, what the acceleration will look like. And once you have that taken care of, then all you need to do is you need to find a corresponding graph for sine functions, and that is what A would look like. So A looks like a sine curve, okay, whereas B looks like a cosine curve. So we will look at that. C looks like a negative cosine curve, and D looks like a negative sine curve. So I will elaborate on this further, right? So this is a good trick for SHM if you want to save time. Also, the answer for this is A and not D. Okay, so that's why I deleted this. So the first thing to realize is we should draw a conventional cosine curve. So if you have a conventional cosine curve, this is what the curve is going to be looking like. So let's say if this is theta and this is cosine of theta. First of all, the cosine curve will oscillate, or it will have a value between 1 and negative 1. Okay? Let me just put it over this. So the maximum value of cosine is going to be negative 1. The maximum value will be 1 and the minimum value will be negative 1. And you should have a good grasp of the unit circle. So if you draw a unit circle over here, then this is 0, 0, and this point is 1, 0. Then this point over here is 0, 1. This point over here is negative 1, 0. And then this point is 0, negative 1. Okay, so this is the unit circle. So at the starting point, so for the unit circle, you have to know that a unit circle is a circle with radius 1, and every point on the unit circle which has a x and y value ends up corresponding to a certain value of cosine of theta and sine of theta. So if I draw an arc over here, and if this arc has a value, if this angle is theta, then the corresponding x and y value for this arc with a radius of 1 will be cosine of theta and sine of theta. Okay, so that's how the unit circle works. Now, when I have a cosine of theta function, I start off at theta is equal to 0, right? So this red line is when theta is 0. Okay, it's just a flat line. So when theta is 0, the corresponding x and y value, which is cosine of 0 and sine of 0, comes out to be 1, 0. So cosine of 0 is 1. Okay, that's why I will start a cosine function at theta is equal to 0 degrees. I'm going to start that function at 1. Then the moment I go up and I go to 90 degrees, you see that the corresponding x value is 0, 1. So you can infer that cosine of 90 is equal to 0. So therefore, I keep coming down, and right there, I get 90 degrees. Okay. Now, when I go even further, I get to 180 degrees. So this entire flat line, as you can see, is 180 degrees. And at 180 degrees, the corresponding x value is negative 1. So cosine of 180 is negative 1. So I go down here, and this is 180 degrees. Bam, and that's 180. Then after that, I make another turn and I go all the way over here. So this is 270 degrees. And what you will see is that at 270 degrees, the corresponding x value is 0. So cosine of 270 is 0. So therefore, when I'm going to draw this curve coming back up, and this is 270 degrees. And then after that, when I make one full curve, this will be 360 degrees. And what you will find is that the corresponding x and y value is that cosine of 360 is 1 and sine of 360 is 0. Okay? So therefore, with this cosine function, I am just going to end back over there. Okay? Now, we have seen before that if I have a function y is equal to f of x, then if I want to graph negative f of x, then I simply just reflect it on the reflect it on the x-axis. So it's sort of like there's a mirror and you're reflecting it on it. Okay? So if you reflect the function, then the function will sort of look like this if you reflect it on the x-axis. So this is the axis on which you're reflecting the red function to get the blue function. And what you're going to be seeing is that this blue function looks very similar to this function over here. So it has the same property, right? It goes like this. Okay? So therefore, we have inferred that this cosine, that this velocity time graph is of the form negative cosine of theta. And we can see from differentiation, or this velocity graph is negative cosine of t. And then we can see from differentiation that acceleration is dv by dt, which is d of negative cosine of t by dt, which is sine of t. Okay? So you will learn this later if you have not learned it now. It's not complicated. Okay? So the acceleration is sine of t. That's the function we're looking for. And so we will go through all of these choices and we will see that option A fits the bill. So option A is looks like a sine function. Okay? So that's why it's option A. In this case, option B, like we have said before, is a cosine function. Option C is a negative cosine function. And option D is a negative sine function. Okay? So if you're confused about this, then just go to Desmos right now and draw all these functions on Desmos. So this is negative sine, this is negative cosine, and this is cosine, and you can see how these functions behave. Okay? So that's why the answer we are looking for is A. So this is the mathematical way to look about it, right? Now the other thing we can do is that we can draw a simple pendulum and then we can visualize things. Okay? So A is the correct answer. So now for the pendulum, the way it's going to work is you're going to draw the pendulum over here. So you've got a pendulum bob that is being suspended from the ceiling. So this is that, and it has a length of L. Okay? Now we can see that in this pendulum bob, we know that the displacement x is maximum at the positive amplitude. The acceleration is minimum at the positive amplitude. And the velocity is 0 at the positive amplitude. Then at the equilibrium position, the velocity is maximum. The displacement x is 0. Okay? And the acceleration is 0. And then at our negative amplitude, the acceleration is positive, it's maximum. The displacement x is negative and it's at its minimum, and the velocity is 0. Okay? And you just have to know that acceleration is proportional to negative x. This is a condition of simple harmonic motion. So if acceleration is high, displacement is low. If displacement is low, if acceleration is high, displacement is low. If acceleration is low, displacement is high. Now, what we're being shown is that we're being shown for the velocity time graph, we're shown the minimum velocity. So therefore, because we are at the minimum velocity, what this actually shows is that what this shows is that the magnitude of the velocity is highest, right? So the magnitude of the velocity is highest, and that's what you get at the equilibrium position. You get, it's the position with the highest magnitude of velocity. Now, because this velocity is negative, we know that the object is going to the left. So you draw your axes over here, y, x, negative y. And so because the velocity is negative, the object should be going to the left. Okay? So we have been seeing over here that when the object goes towards the left, like this, then in this case, the velocity will be going, the velocity will be going from its minimum value to 0. So we saw that at our amplitudes, the velocity becomes 0. Okay? But what we can see is that the acceleration is going from 0 acceleration to maximum acceleration. So the acceleration must be rising. Okay? That's the first thing for these functions. So that means that automatically this is taken out. Okay? D is taken out because the acceleration must be rising, and this shows the acceleration to be falling. B is taken out as well because the acceleration must be rising, but over here that's not the case. Okay? And then after that, what happens is that when the velocity reaches 0, so we know that at this maximum amplitude, the velocity becomes 0 and the acceleration becomes maximum. Okay? So when the velocity reaches 0 at this point, the acceleration should actually be at its maximum position. Okay? And if you see, the only function that sort of does it is a. Okay? Because first of all, the acceleration is rising, and then the acceleration is maximum just when the velocity is 0. Right? Actually, even C does it. So we can sort of move through that and look at things now. Okay? Now, when the acceleration reaches maxima, the pendulum bob is going to go all the way back. So, the pendulum bob, what we've seen is it starts over here, it goes to the maximum, then it goes back, and, it oscillates in this way, right? So, let me sort of clear some of these things. Okay. So what we're seeing over here is that, first of all, the acceleration is rising. At this negative amplitude, the acceleration is maximum and the velocity is 0. Okay? So the acceleration is rising and the magnitude of the velocity is falling because at our maximum amplitude, velocity must be 0. Okay? Now, after this, the pendulum starts to move back. And what you begin to see, right, is that once the velocity is 0 and the pendulum moves back, then, once it's moving back to the equilibrium position, the velocity is rising and the acceleration is falling. Okay? And so, because of that, you're going to get a fall. So, because of that, when the velocity is falling, because of that, in this region, when the velocity is rising, then the acceleration should be falling. And once again, what's happening is that when the pendulum is going back, the absolute value of the velocity is rising, but the acceleration is going from maximum, right? The acceleration is going from maximum to 0. Okay? So the acceleration is falling and the velocity in this point is rising. Okay? Now, as we have seen, it actually cannot be C. And the reason is because, like we have seen before, the pendulum is going to start by moving to the left. So when the pendulum starts, we know that at the equilibrium position, the acceleration is always 0. So that's why the acceleration should start at 0 and not here. So this is taken care of. Okay? So this is because the acceleration in a simple pendulum we have found is negative g sine of theta. At the equilibrium, the theta ends up being 0. So acceleration is just negative g sine of 0, which is 0 meter per second squared. Okay? So when you're doing these things, just visualize the simple pendulum and look how to do those things. Or you can look at the mathematical way, looking transformation of functions. Personally, I prefer the mathematical way. It's faster, and it's like it just seems to be better, right? But you might find other ways better, so you can choose which one you like. Okay. Now, we can look at another question, right? So in this case, in simple harmonic oscillations, which two quantities always have opposite directions? So for this one, we have to look at our simple pendulum, right? And actually, the simple way to look at it is you just need to remember the defining condition of simple harmonic motion. So in simple harmonic motion, we know that acceleration is negative omega squared x, and that acceleration is proportional to negative x. So if acceleration is high, the displacement is low, and if the displacement is low, and then if the acceleration is low, then the displacement is high. So that's why if you look at quantities which always have opposite directions, there must be acceleration and displacement, okay? These two quantities must always have opposite directions, right? So if you see, then that is question 7 right there. All right. Now let's move forward, right? And let's look at question 8. All right. So in this case, the graph shows the variation. So the graph shows the variation with time t of the velocity v of an object undergoing simple harmonic motion. At which point does the velocity, at which velocity does the displacement from mean position take a maximum positive value? Okay. All right, so this one you just have to, we can look at our simple pendulum. So this is a simple pendulum over here. I'm going to draw the 3 different states in the simple pendulum. So we draw the 3 different states over here. Okay. Now, as we see with these 3 different states, we know that at the equilibrium position, the acceleration is 0, the velocity is maximum, and the displacement x is 0. At our positive amplitude, you have maximum x displacement, the velocity is 0, and you have the minimum value of acceleration. So as you can see, a is proportional to negative x. So when a is very high, x is very low. The other way around. What we see over here is that when a is very low, x is very high. All right. And at our left amplitude, you have the minimum value of x, but you have the maximum value of acceleration. And we know that the velocity is 0. Okay. Now, in this case, what's happening is that the velocity is going from 0 to negative. So because the velocity is falling, we can infer that the object is going in the negative x direction. Okay? So if if velocity increases, object is going in the positive x direction. If the velocity decreases, object is going in the negative x direction. So that's why you have this over here, and the first thing is going to be that the object will go to the left. Okay? Now, once the object goes to the left, this has to be the other way. So we start off at velocity v to be 0, right? So the velocity is actually 0 at the maximum amplitude. So we start off over here, right? And what's happening is that the object is going to the left, so the velocity is decreasing, which is why you get this displacement, this movement. Okay? Then after that, what happens is that the object is still going to the left, so the velocity is still negative, but it would end up going off to B, right? And we know that in this case at B, the velocity is 0 at the minimum amplitude. So at B, you're at your minimum x displacement. Okay? Now, after this, you'll go back to the equilibrium because you have to make one oscillation. So the starting and ending point of the oscillation should be the same. So when you're going back, the object is going to the right, which means that the velocity should be rising. And we know that at the equilibrium, the absolute value of the velocity is maximum. This is absolute value. So that's why you have a maximum velocity at C. And then after that, you're going to be going back. So after you reach the equilibrium, you're going back to the starting point. So remember, we started off from the maximum amplitude. And the velocity at the maximum amplitude is 0. So you end up at 0. Okay? So this is the color-coded way of how the pendulum is moving. And they're saying at which velocity does the displacement from mean position take a maximum positive value. So we know that in this graph, we know that you have maximum positive value at 0, at this time is equal to 0, or at this time is equal to D. Actually, yes, at 0. Because you start at 0, you're at max x. So if you look at which options are available, there would be D. Okay? That's going to be the answer for this. It's going to be D. Right? Okay, so that's question 8. And now we can move on to question 9. Okay? So in this case, let's see. So the graph shows the variation with position S of displacement x of a wave undergoing simple harmonic motion. So you have got position S of the displacement x of a wave of a graph undergoing simple harmonic motion. Okay. So position S of the displacement x. Okay, so position can sort of relate to distance. And as we know, distance is a scalar quantity. So that's why you leave it as positive. And displacement, because it is a vector quantity, then displacement can be negative as well. So this is the graph between your displacement and position. Okay? As we can see over here. So now they're saying, what is the magnitude of the velocity at the displacements of x, y, and z? Okay. So we look at the simple pendulum again. This is our simple pendulum. And what we can see, first of all, is that we start off where displacement x is equal to 0. Okay. So displacement x at this point is 0, and then the displacement x would be falling. Okay? So in this case, what's happening is that the displacement x is falling. So you're going from 0, and then you're going to the negative x direction. Okay? That's how the displacement x is working. So if I can color code this, so the first option shows that you're starting off at your equilibrium where x is equal to 0 or displacement is 0. And then you're going to this point over here. So at this point, what we're seeing is that the displacement is the minimum because at your negative amplitude, you have minimum displacement. Okay? Then after that, to make the oscillation, the pendulum bob is going to go back up. So it's going from the negative displacement over here, it's going back to 0, so you get this increase in displacement. Then after that, the pendulum is going to go to the maximum amplitude. So the displacement at the maximum amplitude is the highest. So that's why you're going to get this at the maximum amplitude. Okay? And then from the maximum amplitude, you're going to go back to 0. So you're going to get this over here. Okay? So in this case, if we look at the specific positions, we know that X is this red position. So we'll call this X. We know that Y was this blue position, so we'll call this Y. And then we know that Z is this green position, so actually Z is going to be at the same place at Y. Okay? So now they're saying, so basically the difference between Y and Z is that Z is approaching the equilibrium position from the left, and then Y is approaching the equilibrium position from the right. Okay? So you can just look at it in terms of the color coding. So in this case, because the red color is going to the left, we can say that because you have X over here, you're going to get X over here. And then according to the color code, if you're taking blue to Y, then, this position should be Y. And then we're seeing that, if green is approaching red, so we drew green over here, then this green should also be a part of the equilibrium. So we see that Y and Z are at the equilibrium, and we see that X is at the left amplitude. This point X is at the left amplitude. So now what we can see is that the velocity at the amplitudes is 0. Okay, so at X the velocity should be 0. You should be at the minimum amplitude. Okay, but what we have seen so far in many of the diagrams we have done is that when you reach this equilibrium position, your absolute value of the velocity is maximum. Okay, so that's why when you look at X and Z, then Y and Z, then in this case Y and Z must have the maximum velocity, and this is the absolute value of maximum velocity. So therefore Y and Z are going to be maximum, and the answer will be B. Okay, now if we wanted to make the question tricky, then if the IB wanted to make questions a bit more tricky for you, then they could have introduced this idea of maximum or minimum, right? So what we can see is that since Y is approaching your equilibrium from the right, then we can see that when the bob approaches Y, it's going in the positive X direction. So because it's going in the positive X direction, we can say that the velocity is going to be positive, and it was going to be the maximum value at positive. Whereas for Z, you're approaching Z from the left side, so the object is going in the negative X direction, which means that the velocity will be the negative or the minimum value, right? So the magnitude of both of them is the same. It is the highest number in magnitude, but the direction would be different. So, if they wanted to make things a bit harder, they could have just said that in this case, Y would be the maximum, and then Z would be the minimum value of the velocity, right? But don't confuse this minimum with the magnitude, right? The magnitude is different. The minimum comes from the sign, okay? So I can sort of say that, let's say that in this case, if you have a car and it's going to the left at maybe 1 billion meters per second, right? Then, you might be thinking that, oh, it's going to the left, it has a negative velocity, so it's like very little velocity, but that's not the case. We're not, in this case, if you take the absolute value, if you just take the magnitude, it's a very high velocity, okay? So in this case, there's a difference between the magnitude and the difference between the direction, okay? And the good thing for you guys is that over here, IB just asked for the magnitude and didn't do much about the didn't go much for the sign. Okay. All right, so that is question 9. So now we can look at question 10, right? Okay, so let's look at question 10 over here, right? So a particle is displaced from rest and then it's released at time t is equal to 0. The particle performs simple harmonic motion. So which graph shows the variation with time of kinetic energy Ek of the particle? Okay, so okay. All right, so the way we do think about it is that since we are concerned about kinetic energy, we are concerned with the velocity, right? So if the velocity rises, kinetic energy rises. So this is what we'll focus on when we look at velocity. So once again, we just make a simple pendulum over here, and we have these positions lined down. Now, in this case, the particle is going to be released from rest, right? So because a particle is displaced from rest, by definition, the initial velocity is 0. Okay? So you can just take off A and C. Okay? Because the initial velocity must be 0. And so if the initial velocity is 0, then the kinetic energy initially should be 1/2 mv squared. So m times 0 squared, which should just be 0. Okay, so all of this is going to be gone. Now, the other thing that you need to know is that because the kinetic energy is 1/2 mv squared, in this case, the kinetic energy won't be negative. Why? Because the mass has to always be positive. And in this case, v squared will also always be positive, right? So mass will be positive and v squared is going to be positive. So therefore, the kinetic energy will always be above 0. So therefore, you can eliminate B as well. So the only option that remains is D. That's the answer. Okay? So when you're doing these questions, just look at the process of elimination first. First we were thinking of, visualizing the simple pendulum. But then that makes things too complicated sometimes. So use the process of elimination and be smart about it, right? So just look at things you can eliminate quickly before you move on. So the answer is D, okay? So that right there is question 10. Okay, now let's look at question 11, okay? So in this case, if you look at question 11, then they're saying what is true about the acceleration of a particle that is oscillating with simple harmonic motion. So first, it is that it is in the opposite direction to its velocity. Second is that it is decreasing when potential energy is increasing. It is proportional to the frequency of the oscillation. And in this case, the other one is that it is at a minimum when velocity is at a maximum. So for all of these statements, we look at our simple pendulum. And, a simple pendulum, once again, is not a perfect example of SHM. It's a good approximation, and it's that's why we sort of look at it. Okay? It's an approximation. Even more than an approximation, it's sort of like, you can visualize it, right? Okay, so once again, we saw in SHM, in this pendulum motion, that at your max amplitude, the acceleration is at your minimum, the velocity is at a 0, the displacement is at a maximum. If a velocity is 0, then kinetic energy is 0. And we know that at our maximum amplitude, you get a max height that we have seen. So the potential energy is at a maximum, or the gravitational potential energy is maximum. Then when you get to the equilibrium position, so we'll make this theta and this is negative theta. Now, when you get to the equilibrium position, the acceleration is going to be 0, the displacement x is going to be 0, the velocity is going to be maximum, and this is the absolute value of the velocity, okay? Because the absolute value of the velocity is maximum, the kinetic energy is maximum, and we know that when you get to the equilibrium position, you're touching the ground, so height h is 0. So because the height h is 0 at this equilibrium position, you know that the potential energy is 0. Okay? Then you go to the left amplitude. So in the left amplitude, our x displacement is at a minimum. The acceleration is at a maximum. In this case, because you have a height h, because you have the maximum height, then you can say that the potential energy is at a maximum. The kinetic energy is 0 because the velocity at this point is 0. Okay? So when you do these questions, you will know all of these things, right? Now, in this case, what we can see is that what is true about the acceleration of a particle oscillating in SHM, right? So first of all, they're saying that the acceleration is decreasing when potential energy is increasing. So B is going to be wrong, okay? So let's see how B is wrong, right? So B is going to be wrong because when you're going in this direction, what you're seeing is this acceleration, ACC, is becoming maximum. And at this point, the acceleration is 0, right? So when you're going in this region, first of all, you're increasing your height. So because you're increasing your height, you're increasing your potential energy. Okay? So because you're increasing your height, you're increasing your potential energy. And we are seeing that the acceleration is going from 0 to maximum acceleration. So therefore, there is a region where, if acceleration rises, then potential energy should also rise. So therefore, B cannot be the case. Okay? There is a region where if acceleration rises, potential energy can also rise. Okay? Now for A, in this case, they're saying that the acceleration is opposite direction to the velocity. So in this case, what we can see, right, is, okay, so let's see how to go about it. Yeah, okay, so we can see it this way, right? Let's say we take this region now, okay? So let's say the pendulum is going down this way. So if the pendulum is going this way, it's going in the positive x direction, so we know that the velocity is positive. And we have seen that the acceleration in this region is also positive. And once again, the reason for this is because in the simple pendulum, we derived that the acceleration is equal to negative g sine of theta. And in this region over here, the theta is going to be negative because you're going in the opposite direction. So this comes from the unit circle, basically. So in this case, if you go up this way, then you go into positive theta. And then if you go down this way, you go into negative theta. So if you're going up, you're going to positive theta. And then if you're going back, you're going to negative theta. Okay? So that's the reason why we call, why we say that theta would be negative. So we have seen that acceleration is negative g sine of theta. And because theta is negative, this is negative g sine of negative theta. And then this just becomes positive g sine of theta. So in this purple region, the velocity is positive because you're going in the positive x direction. And the acceleration also ends up being positive. Okay? So therefore, it's not the case that the acceleration is opposite to its velocity all the time. There are some regions where that is the case, but not in all regions. Now for C, it is that they're saying that it is proportional to the frequency of the oscillation. So this one is wrong. And the reason is because, we derived that acceleration is negative omega squared x. And we also saw that the acceleration is negative k by m times x. So we were able to see that in this case, we were able to understand that omega squared is equal to k by m, right? So omega squared is equal to k by m, and so we could see that omega is the square root of k by m, and we knew that omega is 2 pi by t, which is square root of k by m, right? And so we were able to derive that t is equal to 2 pi square root of m by k. Okay? And in this case, if this is 2 pi by t, what you can also do is that we know that frequency is 1 by time period. So 2 pi by t just becomes 2 pi f. So 2 pi f is the square root of k by m. And so in this case, we can see that the frequency is the square root of k by m, and then this is 1 by 2 pi. So as you can see, the frequency only depends on the spring constant for a mass spring system and only on the mass. So we're talking about a mass spring system over here. Okay, so for a mass spring system, the frequency depends on the spring constant and the mass. All right. So therefore, the acceleration is not proportional to the frequency of the oscillation. So that's why C is wrong as well. Okay. The frequency is only proportional to the spring constant of the spring and the mass, right? So once we get to that point, we can simply end up saying that C is wrong as well. And so that only leaves us with option D. And option D also makes sense because if we look at our graph for this simple pendulum, we see that when acceleration is 0, the absolute velocity becomes maximum. So when the acceleration becomes 0 at the equilibrium position, the absolute velocity becomes its maximum. And so because of this, option D is correct. Okay. So that's question 11. Now we can look at question 12. All right, so let's see how to go about it. Okay, so the way we look at it is that in this case, this should actually be from the point. I think that got taken out. So an object performs simple harmonic motion about a central point. The object has velocity v and acceleration a, and it has a displacement x from the point. Which ratio is correct? So you're performing SHM along a central point. You have a velocity v and acceleration a, and you have a displacement x from the point. So which ratio would be correct? And these are the ratios. So the way you can think about it is, once again, we go to our good friend, which is the simple pendulum. So this is our simple pendulum, and let's draw it over here. So when we reach this point of the simple pendulum, we're going to be seeing that this is a certain point. Okay, this is a central point. The object is performing simple harmonic motion, so therefore you're going to get this sort of pendulum movement that's taking place in this SHM, or in this approximate SHM. It's not, pendulum, once again, is not, pendulum is not a, it's not a full SHM, right? It's like it's sort of like an approximation, but not that accurate as one, right? Okay, so the object has velocity v, acceleration a, when it has a displacement from point x. So now they're saying what ratio is correct. So x by a, x by v, x squared by a, and v by a, right? So for this one, for this one, you just need to know this defining equation of SHM. So in simple harmonic motion, the acceleration is negative omega squared x. So therefore, what you can say is that x divided by a, right? X divided by a becomes negative 1 by omega squared. And negative 1 by omega squared is a constant. which is why x by a becomes a constant. Okay? So a is negative omega squared x, and therefore x by a becomes a constant, right? Because omega is a constant. So, so that's how we would look at it. And this actually helps us when we look at some physics questions. So, sometimes what can happen is that you can be given this graph on the perhaps on a test or an examination, where you have this graph of acceleration and x. So this is what the graph is. So this is your acceleration graph, and then this is your displacement graph, and then this is the inverse relationship. So we know that the acceleration is negative omega squared x. So if you sort of think about it, this sort of looks very similar to y is equal to mx, right? So in other words, what this means is that if you take the gradient of this, so let's say if you've got a certain rise and then this is a run, if you take this sort of gradient, then this gradient will give you this constant, which is m. Sorry, actually it's negative omega squared. Okay? So in other words, the gradient of this acceleration displacement graph is negative omega squared. Okay? That's what the gradient comes out to be. And you could perhaps get some question on that, right? So it's always good to know that this is a very important equation, and the other equation is acceleration is negative k by m times x. The acceleration is proportional to negative x, and you should also know those kinetic energy, potential energy graphs as well, right? So that's question 12, done and dusted. So now we can look at question 13, right? So let's see all that is there. So now let's look at this example over here. Okay. So in this case, what you have is that a body, right? It undergoes one oscillation of simple harmonic motion. A body undergoes simple harmonic motion, right? So in this case, which graph correctly shows the variation with displacement x of the velocity v of the body, right? So once again, what we can see is we can draw the simple pendulum. So this is a good diagram, right? So let's just let's take this diagram. So yeah, so once we get to this point, what we can clearly see over here is the following thing, right? And then I can erase this over here. Okay, so the following, you can see this following thing over here. So we know that so we are looking at the variation of velocity with displacement x, right? So we know that when the velocity is the maximum, then the displacement x is 0, right? Because you're just at the starting position. So when velocity is at the maximum, the displacement x must be 0. And when we know that at the amplitudes, when the velocity is 0, the displacement x can either be maximum, right? Or if the velocity is 0, the displacement x can either be minimum. Okay? And so all we need to do is we need to look at these things, and we just need to see which graphs fit the bill and which graphs don't. So as you know, when x is 0, velocity is maximum. So in this case, that's not the case, because when x is 0, velocity is 0, so that's wrong. Okay? It cannot be b, because when x is 0, the velocity is also 0, so that's not the case. So now we can look at these two conditions between a and d. So for a, we know that when x is 0, velocity is maximum. When x is 0, velocity is maximum as well. Okay, so now all we can do is we can test the second condition that we laid out. So this states that when the velocity is 0, x is maximum or its minimum. So we can see that at this point the velocity is 0, but clearly the minimum value of x, as you can see over here, but in this case clearly the maximum value of x. So this is maximum x, right? So we see that at the maximum value of x the velocity is not 0, right? So at max x the velocity is not 0. And what we saw over here is that when x is maximum or minimum, velocity must be 0. And so similarly over here, when x is at minimum, the velocity is not 0, which is why option C won't work. So by elimination, you go to option A. Okay, so for example over here, when x is at its maximum, the velocity becomes 0. When x is at its minimum, the velocity becomes 0. And then over here, when velocity is 0, and then over here, when x is 0, velocity is maximum, right? So we looked at the conditions in the simple harmonic motion and in the pendulum, and based on those conditions, we got answer A. Okay. So yeah, for these type of questions, always look at the simple pendulum and use the process of elimination. Okay. Now let's look at question 14. So in question 14, the diagram shows the variation of velocity v, right? It shows the variation with velocity v. It shows the variation of velocity v with time t for an object performing simple harmonic motion. So this shows the variation of velocity with time, as we see over here. Okay. All right. So, one second. Okay. So if the object is showing the variation of velocity with time, then they want us to find how acceleration varies with time t, right? So once again, we just so this one is simple. This one is more simple as a question. So what you can do is that you can just you can view it mathematically, right? So we know that the velocity function actually resembles a sine curve. So this is going to look like a sine curve. Okay. So I've explained this before as well in some of the MCQs that we just did. And if you have any doubts on that, then you can look at Desmos, right? Main thing is that you draw the unit circle, and what you see is that in a unit circle, you draw these points 0, 0. In the unit circle, you draw these points over here. So this becomes 1, 0, 0, 1, negative 1, 0, and then 0, -1, and then this is the center. And you can just you can say that at this purple line theta is 0, then at this green line theta is 90, at this dark blue line theta is 180, and then at this red line theta is 270, and then once it goes back again at this blue line theta is 360. And in a unit circle, you also have to know that for an arc with an angle of theta, the corresponding value, this x, y value, corresponds to cosine of theta and sine of theta, right? So I've explained this in depth, right? Even in the concept videos, okay? So the main thing you will see is that this y value, this v value is going to represent a sine function. And so we know that the acceleration is going to be the change in velocity, delta v by delta t. So you can use these derivatives. So the acceleration is dv by dt, And we know that the velocity is sine of theta. That's what the form is. So d by dt of sine of t, which comes out to be cosine of t. And then if you look at all of these functions, you will find it cannot be a, because a is of the form of sine of theta, so it's not a. In this case, it's not c as well, because c is of the form of negative sine theta. So you can graph this on Desmos and see it. D is also not the case, because D looks to be the form of negative cosine of theta. Okay, we want to find the function cosine of t. That's what we are looking for, and that's what B is. So if you look at the unit circle, you can see that, in this case, when theta is 0 degrees, when this theta is 0 degrees, the x value is 1. So when theta is 0, you're at 1. Then when theta goes to 90, the x value becomes 0. So therefore at 90, you get to 0. And then when theta becomes 180, you go to negative 1. The x value becomes negative 1, which is why you get over here. This is 180. And then from 180, when you go to 270, the x value is once again 0, which is why you go back to 0 at 270. And then after you go from 270, then from 270 you go back to 360, as we have seen, and then this becomes 360, and we know at 360 the value is 1, 0, and so this shows one period of the cosine function. So the cosine function is going to basically vary with x. Okay, so we know that the values of x, y on a unit circle of radius equals 1 corresponds to cosine of theta and sine of theta. So based on this, we can recognize these functions. Okay, so that's how we would be looking at it, right? Now, in this case, you can probably see if they allow you, if they would allow some sort of calculator for paper 1. For example, if you have a graphing calculator, then you can graph these functions, but I don't think they would allow it. So you need to be able to visualize these functions, and it's not hard, in the sense that if you just spend maybe 10, 15, 20 minutes to understand the concept, then you can understand them, right? Okay, now in this case, we can look at a thing over here. So for a body undergoing simple harmonic motion, just 1 second. So this is question 14, and then this is question 15. Okay. So for a body undergoing simple harmonic motion, the velocity and the acceleration, in this case, so as you can see, this question is exactly the same as what we did in one of our previous questions. Okay, so we can once again just graph. We can graph it using our SHM. We can visualize it using our simple pendulum. So for a body undergoing simple harmonic motion, the velocity and the acceleration are always in the same direction, are always in opposite directions, in the same direction for quarter of a period, or in same direction for half a period, right? So for this, you can once again just visualize this over here. So let's say that if you drop this, if the pendulum bob is going to the left, so we can see that in this region theta is positive, so then the acceleration is negative g sine of theta, and because theta is positive, then the acceleration over here just becomes negative. And we know that because the object is going to the left, then the velocity is negative because you're going in the negative x direction. Okay. Now when you enter this region, then the theta becomes negative, right? So we can see over here that the acceleration is negative g sine of theta, which is negative g sine of negative theta, and negative g sine of negative theta just becomes positive g sine of theta. So therefore in this direction acceleration becomes positive. But what you see over here is that the object is still going to the left, so the velocity stays negative. Okay? So therefore, when you're going from here to here, the acceleration is negative and the velocity is negative, so it's in the same direction. Then when you're going from here to here, the acceleration is positive, but the velocity is negative, so that's not in the same direction. And then because we're measuring this for one oscillation, then you're also going to have to show the pendulum bob coming back. So when the pendulum bob comes back from the negative amplitude, we can see that the acceleration will still be positive, right? Because this is negative g sine of negative theta, that's what acceleration is, and that's going to be positive, right? But in this case, and also the velocity is also positive because the pendulum bob is going in the positive x direction. So therefore, when you're going from here to here, the acceleration is positive and the velocity is positive. Okay? And then in the last one, what you can see is that when the bob is going from here to here, the acceleration becomes negative because theta over here is positive. So this is negative g sine of theta, which becomes negative. And the velocity stays positive because the object is going to the right in the positive x direction. So that's why when you're going from here to here, the acceleration is negative, but the velocity is positive. So as you can see, the acceleration and velocity are in the same direction for two sections, and they're not in the same direction for two sections, right? And so as you can see, we were also analyzing only one period. So this is one period when the pendulum starts at a position, goes all the way to the left, and comes back. Okay? So once we have this thing over here, we can see that the acceleration and velocity are in the same direction for two regions, and they're not in the same direction for two regions. So that's why, if you take the ratio, this is 2/4 or 50%. So that's why the velocity and the acceleration are in the same direction for half the period. Okay? So that is what you would see over here. Okay? Now, this is another mathematical way to think about it. So in this case, let's say if the velocity is a sine function, right? So if velocity is a sine function, and then let's say that the acceleration, so if the velocity is sine of t, so if this is t and this is v, if the velocity becomes a sine function, then so if velocity is a sine function, then the acceleration is d by dt of sine of t, which becomes cosine of t, right? So I think so the way you can see it in this case is that you can draw some lines over here, right? And so let's say that if this entire line is like one period, right? So if this line becomes one period, let's draw some lines where they are intersecting, or in this case where these functions reach 0, right? I think this would be more of a long shot, but what you would be doing is, you would be seeing both of these functions, and then you would be comparing them to see when they're in the same direction and when they're not. Like when they're both positive and they're both negative, and then you would take the ratio over the time period. So I think, you don't need to really think about this one. I don't think that's necessary, right? So if you want to do these questions, just visualize the simple pendulum, right? So you must be very comfortable with understanding the simple pendulum, okay? And you need to know, how the acceleration, velocity, displacement, kinetic energy, potential energy, you need to know how these all vary at different points. So there are 3 points you need to remember: the maximum amplitude, the minimum amplitude, and the equilibrium position. And you just need to know how these vary. You need to know the important equations. So you need to know that the acceleration is negative omega squared x. The acceleration is negative k by m times x. You need to know that t is 2 pi square root of m by k. And in this case, you would need to know that the time period is 1 by frequency. And so you need to know these things over here. And the main thing is visualization. So you must be very good at visualizing the simple pendulum, right? And you need to know a simple pendulum is not a perfect example of simple harmonic motion. It's an approximation, but it's good for visualization purposes. And so you must be able to know that. And then after this, you just need to be able to know a unit circle, right? Sine curve, how to draw a sine curve, cosine curve. Then, those reflections where, you have to graph f of x and negative f of x. So you need to have a good background in trigonometry, right? So sometimes instead of visualizing with a simple pendulum, you can just use math and do it that way, okay? So main idea is visualization. That's the main thing that you should be able to do in these questions, okay? So with that, we're done with the topic-wise MCQs for simple harmonic, and we'll start with paper 2 later on, okay? All right, good luck.